You've probably heard about the tragic story of OceanGate's Titan submersible. It was a small diving vessel designed to explore the wreckage of the Titanic, 3,800 meters under the sea. But how did this submersible and the systems on it actually work? There are a lot of interesting systems on the Titan, from propulsion to communication. Some that worked, some that tragically didn't, and one that was even designed to dissolve underwater. I'm Ryan, and welcome to Zeroth. This channel normally focuses on sustainable energy and transport, but given that this was an electric vessel that operates out at sea, where a lot of energy projects are now being deployed, I thought you'd probably find this interesting. Let's start with a quick overview. The Titan submersible was designed to go as far as 4,000 meters underwater. The pressure that deep is equivalent to an elephant standing on one leg, and then 226 more elephants climbing on top. This pressure, combined with the darkness, cold, and difficulty communicating with the surface, are part of what makes deep sea exploration so difficult. The whole system weighed approximately 10 tons and was primarily made of a few core components, the largest of which was the carbon fiber hull, which was the eventual failure point of the vessel and sadly resulted in all those aboard losing their lives. The hull was 5 inches thick and somewhat reminds me of the carbon-wound hydrogen storage tanks starting to be used in hydrogen vehicles. However, there are some very important differences here. Firstly, the hydrogen storage tanks have a metallic liner to help contain the hydrogen, and secondly, these tanks undergo an immense amount of safety testing. This includes tests for fatigue and destructive testing to find out the structure's limits. Once these limits are found, it can be ensured that they are never reached during normal use. This kind of testing was never done with the Titan submersible. Because of this, repeated exposure to high pressures meant that on the 7th dive to the Titanic, it imploded. To demonstrate this effect, here is a railroad tank imploding when put under a vacuum. This is caused by the pressure outside being much larger than the pressure inside. The implosion for the Titan would likely have been even quicker. This left me wondering what was actually put in place to stop this happening. The first way to prevent failures like this is to create a virtual model of the submersible and test its limits. However, carbon fiber is notoriously hard to model because it is not one single block of material. It is instead lots of thin fibers that are interwoven and cured together. This also means there are many ways it can weaken, as layers shift and come apart from one another. Without any destructive testing to fully test the limits of the Titan, these models were just not enough. This is where the second system was meant to come in. Aboard the Titan, there was a real-time acoustic monitoring system, which OceanGate claimed could detect buckling of the carbon fiber hull prior to a catastrophic failure. According to a patent held by OceanGate's CEO Richard Stockton Rush, this used multiple small sensors such as ultrasonic microphones and strain gauges to monitor vibrations in the carbon fiber. This data would have been collected at regular intervals and sent to a centralized system for storage and analysis. At this point, it should have been able to assess the health of the internal and external structure, and predict failure conditions. However, this type of testing is a relatively new field, and clearly wasn't enough in hindsight. In fact, an open letter from the Marine Technology Society said they had concerns the Titan design could result in catastrophic negative outcomes. Not only was the use of carbon fiber concerning, but so was the tubular shape, which is much worse than a sphere at distributing the pressure from the weight of the ocean. Next, we have the end caps of the Titan, which were made from titanium and secured onto the main hull using 18 bolts, giving passengers no way to get out from inside. The viewing window was also reportedly made from a material that was only certified down to 1,300 meters, just a third the depth of the Titanic. These components were all tested together on a 1/3 model in collaboration with the University of Washington, at which point an ex-employee called David Lockridge expressed concerns that the scale model of the sub had revealed flaws in the carbon fibre under pressure testing. But aside from the fatally designed hull, how did the Titan submersible actually operate, or know where it was going? After an initial briefing, the first step of a Titan launch was to deploy the docking station from the main ship. This is why the Titan was actually classified as a submersible rather than a submarine, because a submarine is able to leave and come back to port under its own power. The docking station would then fill up its ballast tanks with seawater, increasing its weight and causing it to plunge 9 meters underwater. At this point, the Titan could detach and begin its descent, whilst the docking station refills its tanks with air and floats to the surface. At the end of the voyage, this process would then be done in reverse. The Titan was carefully balanced, so it wouldn't float or sink unless the electric thrusters were activated. It had 4 electric thrusters in total that could propel it up, down, forwards and backwards, or rotate it around. These were from a company called Innerspace, and are specifically designed to operate extremely efficiently in both forward and reverse directions. The power for these motors would then come from an onboard battery system, similar to those found in an electric car. The controls for the submersible have come under some significant scrutiny in the media, with the main focus being on the games controller used to direct the vessel. However, as strange as this sounds, it's actually quite common in military applications too, due to their ease of use, durability, and accessibility. Game controllers are currently used all around the world to control anything from explosive disposal robots to Virginia-class attack submarines. The Titan also had touchscreen displays, which would have shown images from the external cameras and text messages sent from the main ship at the surface. However, neither of these things are easily achieved deep down into the sea. For the cameras to pick up anything in the dark depths of the ocean, you need some pretty serious lights. That's why the Titan had 40,000 lumens of external lighting, which is about 40 times as much as a car headlight. Receiving messages, however, uses a much more elaborate system. The communication and tracking for the Titan sub were both done using what is known as an ultra-short baseline acoustic system. Acoustic pulses could then be used like Morse code to send messages. This is how the Titan sub was directed to the Titanic wreckage on previous voyages, as it had no navigation system of its own. But that begs the question, how did the surface ship know where the Titan sub was located? Well, that's where the acoustic positioning system came into play. First, the surface ship would emit an audio frequency from a transducer. When the transponder on the Titan received this, it would then respond with a similar signal, which would be picked up by the surface ship. By measuring the time taken to receive a signal, the surface ship could work out how far away the Titan was, and by having multiple transducers on the ship, it could also work out the direction the audio wave came from. By combining these together, it would know where the sub was located, and send messages to direct it to the wreck of the Titanic. Because we all know the tragic outcome of the last Titan voyage, the safety systems aboard may seem pointless. And given the corners that were cut when designing the hull, in many ways they were. However, let's see what safety systems were aboard that could have helped the passengers if the emergency was different. It is first important to consider that in all possible emergency scenarios where the passengers remain alive, such as a power cut or loss of communication, the best option would always be to return to the surface. However, if there was a fire, this would require extra action. This is why there was a fire extinguisher on board and smoke masks for all passengers. Because resurfacing would have been the priority, there were 7 systems aboard to help the Titan reach the surface. These included powering the electric thrusters, inflating an air balloon, and dropping lead weights. However, one of these systems was actually a dead man's switch. This means that it would have worked even if everyone aboard had passed out. This dead man's switch was made using a material that would dissolve when exposed to the salt water. This meant that after around 10 hours of diving, the material would completely dissolve and release sandbags from the bottom of the sub. Because of this lost weight, the sub would have buoyancy and start floating towards the surface. None of these safety systems would work, however, if the Titan didn't have a fresh supply of breathable air. The key requirement for that is to provide oxygen to the hull and remove carbon dioxide. The oxygen was supplied by onboard tanks, and the carbon dioxide was likely removed by a CO2 scrubber. A common choice for this is sodium and calcium hydroxide, which trap the CO2 in a chemical reaction to ensure the air is breathable. This tragedy really shows that the ocean must be respected during all projects within it, from energy to exploration. I hope from all of this that you learned something new and found this video interesting. If you did, I'd really appreciate you subscribing to my channel, as you'd probably like some of the other videos I make, like this one about a new micro hydro turbine.